based reasoning. So I'm going to use CBR for short. So whenever you see CBR, know that we are referring to not a model of byte, but rather case-based learning, which is a subset of your instance-based reasoning. So it's case-based, one word. Don't get confused. So when we talk of case-based learning, what we're actually telling you is it is a kind of a paradigm, okay, that is based on lazy learning method. And they classify new queries by analyzing similar instances while ignoring instances that are very different from the group. Can I repeat? So if you think of this, that means that instances are handled on case-by-case basis. That's my own interpretation, okay? So what we talk about when we discuss case-based reasoning is that it is a learning paradigm that is based on lazy learning method, whereby new instances are classified by analyzing what? Similar instances while ignoring instances that are different from the query. So if you remember what we studied when we looked into an inductive and a deductive system, which we call the equation solver, what we said was that an inductive system takes some sets of input, right? Passes it through some inductive system, and then the output will be either it will classify or it will say it does not know what you are talking about, right? So this is what happens here. In this case now, what we are talking is it will actually look at instances that are based on previous instances that must be similar. So if you look at it here, the output will look like this. So if you put the output will be like this. Output will be equal to 1 when they are similar, right? Say an instance A, if instance A is exactly equal to what? Instance B. Now, usually we say we don't use this, okay? It's a comparative operator. So anyway, but just take it like that. If they are exactly equal, right? Otherwise, output will be what? 0. Output will be what? 0. If the instance A to be classified is not equal to the instance B. So that is what we have here, okay? Now, another interesting thing about case-based learning is that instances are not represented as real valued points, but instead they use what we call what? Rich symbolic representation. Now, here I try representing it as what? Real valued points. Actually, I use discrete valued here, in which I say 1.0 makes it real, or 0.1, whatever. But if you see here, this is not how we represent instances in what? Case-based reasoning. So we use some symbolic representation. And this CBR has been applied to problems such as what? Conceptual design of what? Some mechanical devices. Based on what? Stored library functions of previous design. And that makes sense because when you want to reason about new legal cases based on the previous designs, you are actually solving this planning problem and scheduling problem by reusing what? Portions of the previous solutions to similar problem. So if you think of model of a car, so there exists some previous instances of some previous functions that actually can be reusable. Example, the way you change gear even in high-end vehicles will still be the same way you change gears in what? A local branded vehicle. And braking will always do the same job, acceleration will always do the same job. And this is what we do when we work on what? A kind of a practical CBR system, which we call what? The Cadet System. We'll get to that in a while. And then this CBR case-based system is heavily utilized when we are working on problems involving planning and scheduling, okay? Because we have to use portions of the previous solutions to similar problems. Now, we will look into a prototypical example of a case-based reasoning. Now we have understood the concept behind CBR. Let's look at a prototype of a case-based reasoning. By the way, prototype can actually be an evolutionary prototype or a throwaway prototype. Okay, so what I mean in this is that A prototype is kind of maybe an unfinished product, right? In which we want to test out the functionality of the product, how it will look like when it is actually finished. So if I want to use an evolutionary product, say I want to get into electric vehicles, I cannot compete with Tesla. So what I will do is maybe I'll try to design mine from scratch, looking into the battery efficiency and some stuff. What I do is, before I actually look into this, I'll need to design a working model. So that working model might not have all the functionality we need, okay, for it to function as a fully automated electric vehicle. But in between, there will be room for improvement, in which maybe I will look at upgrading the battery, I will look at integrating sensors into it and or whatnot. So in this case now, a prototypical model is called the Cadet System. So we look at now what? A prototypical example of what? Of CBR. So the Cadet system, which we are going to discuss, is actually, or we say the Cadet system employs a case-based reasoning to assist the conceptual design of simple mechanical devices, such as what? Water faucets. In conceptual design of some mechanical devices, such as what? Water faucets. So, if I may ask you, what is a water faucet? Anybody? What do you think a water faucet is? This is simply telling you it is a water tap. And you know how a tap looks like, right? I don't know how to draw, but say this is the handle and some tap is there, right? So you can turn this to some angle and then, I don't know, and water will gush out before I go and draw something else, right? So, if you look at this in the water tap, what comes to your mind is there will be some water in the overhead tank, in which if I increase the quantity of water, then the pressure, the pressure also increases. So I have this experience, okay, where everyone knows that it's a simple, straightforward example. That the more the quantity of water in the water tank, the greater the pressure, right? Hence, your mom can actually tell you that better go and pump the water because she knows that the pressure has reduced. So similarly, this Cadet system employs what? A library containing about 75 previous design and design fragments to suggest conceptual designs to meet what? Specification of new design problem. As you have seen, you see the water tap, right? Most of them, previous water taps, at least I can remember when I was in Bangalore, most of the water taps, in the house I stayed, we never had a water filter, right? And many of them were not made of steel. It was either made of bronze or some local material. Now, if you look at that and I want to improvise on that, I need to look at specification of previous water faucets, right? And think of how I can actually improve this so that it will be able to minimize, leakage of water, right? So the same thing is applicable here, that in this Cadet system, each instance is stored in memory, okay? So before I get into that, I said that it uses what? A library, as you know, definitely, collection of approximately 75 previous design patterns, right? And design fragments to suggest conceptual design of a new water faucet, obviously. And in this instance, for me to actually look at the previous design, I have to store it, right? So we store it in a memory, right? So, and this memory is represented by describing both the structure, both describing it structurally and what? Qualitatively. So, in this case now, if a new design problem arises, then it can be presented by specifying the desired function and requesting the corresponding structure. Now, you can actually visualize what I'm telling you. The problem can be illustrated by using a figure. So you can visualize the figure now as a tap, right? So let's look at an illustrative example of a stored T-junction pipe. So an illustrative example. here I'll say where Q1, where Q is what? Quantity of water flow. Quantity of water flow. And then T is your what? Your respective temperature. Now, you can imagine that in every faucet, you know, there are two kinds of nature of water that can flow in that, right? You will not get ice water anyway. So you get either hot water or you get cold water, definitely. In most of your washrooms, you get geyser, right? I mean, water from the geyser will obviously be hot, unless you didn't turn it on. And then the normal one which you want to use to dilute it will be cold water. So in between, if hot water is flowing and cold water, okay, definitely. Okay, let's say this way. Hot water flows, cold water flows. What you're going to get a lukewarm water, right? Or a mixed water. So in this case now, we now represent this function as what? Quantity 1. So we have a function. Quantity 1 that flows down, quantity 2 that flows up, leading to quantity 3, right? That's what we saw there. So Q1 and Q2 leading to Q3. But pay attention here. There is a sign that is assigned to them. I'm using this repetitively. There is a sign that is attached to it. So you can see the positive sign and you can see the negative sign there. So where the positive sign says what? An increase in this quantity, right, leads to an increase in this. And that makes sense. Because if you open the tap completely, right, what happens is that the water will rush down faster, right? So whereas if you reduce the tap, right, the water tends to drizzle, okay? So it tends to drip, it will drizzle through the tap. So you see, this is what we are actually talking about when you have this positive notation. Now we see, would there be a situation in which an increase in one quantity leads to a decrease in another, right? So what do we do in such a situation? And if you notice here, we have seen quantity 1, please look carefully, and quantity 2, quantity of water flow, and quantity of water flow down, quantity of water flow flowing up, leads to quantity of water flow down. So what it means there is, for this corresponding what? Quantity of water, we get an equivalent what? Quantity of what? Temperature that mirrors the same behavior. Such that, you see here, this is your temperature 1, and again you get your what? Temperature 2. And you see that increase in both also leads to increase in temperature 3. Right? Hence, again, they have what? Positive sign. The reverse is the case. If the quantity of water here is, the temperature at this maybe it's like 100 degrees, and temperature here is at maybe like 20 degrees or 0 degrees, you tend to get what? A lukewarm water. Fine. Now, that's what we just said here, okay? That the quantity, the function is represented in terms of what? The qualitative relationship amongst water flow levels and the temperature between the input and output. So you can see that this you can call the input and this is the output. So this is my output and that's my input, right? IMP. Fine. Hence, when you see a negative notation, it tells you that it is the reverse. And you see there that the quantity Q, you can see the Q1, Q2 or whatever, so you can call it QC or QA, refers to the flow of what? Cold water. Now, I have just shown you some quantity of water which flows. So, now, we can have instances, we say, let me just define it. So, giving, instead of where, I will say giving QC to be what? Quantity of cold water. Of what? Cold water. Then we can have QH to be what? Quantity of hot water. Now you have TH to be what? Temperature of what? The hot water. And then TC to be what? Temperature of what? Cold water. So you can also have maybe Tm to be temperature of mixed water, right? Temperature of mild or mixed water. So we can call it mixed water temperature. Now, what you can see is that, and we have another variable CT, which is what? Control signal for what? Temperature at the input. At input. Right? Now, we are telling you that if you are given a problem specification, okay, how will the structure look like? Because we have seen a previous structure, right, in which you can actually see that as the quantity of water flows down and this flows up, okay, as temperature from T1 to T2, that directly influences the temperature T3. But in this case now, if you are given a structure, if you are given a function, can you actually decode the structure? So this is a practical situation. What would the structure look like when given what? The function. When given the function. So what is the function? Now we can actually see that there are what? Two control signals, CF, okay, so it's called CT and CF, okay? The temperature and that are the faucets, okay? Quantity of hot, this quantity of cold, then temperature of hot, and similarly, temperature of cold, right? So we actually start with this. I made it alter. So let's say here, quantity of cold first, quantity of hot next, temperature of cold, and temperature of hot, okay? And that this, you see here, you just watch closely. So this goes to this, right? Right? And similarly, this control signal also goes to the quantity of hot water. Invariably, again, this quantity goes to this, and this goes to that, right? So, from here now, we now see that the quantity of cold water, the quantity of mild water would be affected by the quantity of cold water that flows into it. Definitely will affect this. So, now, as the quantity of cold water increases, yes, what happens now? And with the quantity of what? Hot water. So we take this hot water. What do you think? We will get what? Mild water. Obviously. Cold plus hot gives us mild water, or which we call lukewarm water. Lukewarm. Now let's try to see the behavior here. So cold, hot, we get mild temperature. So this is mild temperature. Now, right? Now you see, cold and hot, obviously there will be a direct relationship, right? Cold and hot gives mild. Quantity of hot gave mild, so no problem, it can be positive. Now, quantity of hot can be positive, but for me to get this now, I need to get quantity of cold water. Now, if it decreases, what does this mean? It means that now we are getting a negative sign. It means that the variable here, okay, decreases as what? The temperature increases. Right? Based on this function, the cadets will search its library of stored cases. Because this is a generalization, a general structure, which I don't know now. The structure might look like the previous, but with some modifications, right? If it looks like the previous with some modifications, what kind of inputs we get into this? What kind of output are we expected to get? So this is a one notation. How about if it looks like this? Maybe we have this, or maybe it looks like this, right? So what if it looks like this? Now we see there are various structures that is possible in this case. So for us to answer this question, the cadet system will now search its library for stored cases whose functional specification match the design problem implicitly. So it has to match it exactly. Otherwise, it will say, I don't have an idea, and I cannot give you a postulate. I cannot give you a probable solution. Now, if an exact match is found, that means indicating that some stored case implements exactly the desired function, then this case can be returned as a suggested solution. So, and then if no exact match occurs, now cadets may find cases that match various subgraphs of the desired functional specification. So, if an exact match is found, say this is the exact match. So this returns it as a structure. Otherwise, what it will look like, the cadet system will suggest subgraphs. So subgraphs might be some portions of this, which might actually be this one, or it can actually be this one, right? So that meets this specification. And with this, we wind up with case-based reasoning. Before we conclude, let's understand how we started. So we started by first looking at a definition of case-based learning in which we define case-based learning or case-based reasoning as a learning paradigm that is based on lazy learning methods, in which we classify new queries by analyzing similar instances while ignoring instances that are very different from the query. And we said that instead of in case-based reasoning, there is no concept such as revalued point. Rather, we have what we call rich symbolic representation. And that CBR has been applied to problems involving what? Conceptual design of mechanical devices, such as what? Your faucets, right? Now, and which is based on reasoning of your previous what? Designs. Now, and this problem, and you solve this problem, and this is usually applicable in problems involving what? Planning and what? Scheduling, by using what? Previous portions of your what? Solution that are similar. And we saw a typical example of that, which is your what? Your cadet system, which we heavily employ in designing of what? Mechanical devices such as your water taps, right? And then we saw that this actually works by examining what? Libraries containing approximately 75 previous design and design fragments that suggest conceptual design to the specification of your new what? Design problems. And we now say that each instance is always stored in memory, okay? So that when a new problem arises, we have to glance through the memory, okay, and then see, or the library, and then see if it exists. And we saw a typical example, which is called a T-junction pipe. And in T-junction pipe, we came across the concepts of your what? Temperature, your what? Quantity of water. And then we now saw that as the temperature at one source increases, the temperature at the other end increases. And we also saw when one temperature increases and the other one decreases, we are able to find out what is actually happening. And then we now saw a real scenario in which what? We want to understand the structure given a functional requirement. And we now concluded by saying that in this case, it's guided to search its what? Library for stored cases that matches the description. And with this, we will look into the next concept, which is your reinforcement learning.